Hello ladies and gentlemen, and welcome to this first in a series of videos during which we will go through the OCR Chemistry A Synthesis and Analytical Techniques paper from June 2017. In this first video in the series we'll go through multiple choice questions and I'll let you into some of the thinking that's gone into my answers that I give, and after that we'll then start looking at the other questions in slightly more detail. So if we make a start, we'll go down and have a look at our first series of questions. So, the chemist compares the rates of hydrolysis of 1 chloropropane and 1 bromopropane in ethanol. What we should be really paying attention to here is that we've got the hydrolysis of haloalkanes, so we're going to be able to identify this via the precipitates formed when we have silver nitrate present in aqueous solution. So we were looking for B there. For question 2, how can a molecule below be described? Well, what they're really saying is, what would we describe these structures as? And what we have that's important to take note of here is a ring system, which immediately tells me that this is going to be alicyclic. This is an aromatic ring. And we can also see a lack of double bonds, meaning it's a saturated compound. So we should be saying that this is an alicyclic saturated compound, which is D. We look at question 3 here. Complete combustion of an organic compound forms 40 centimeters cubed of carbon dioxide and 40 centimeters cubed of water vapor under the same conditions of temperature and pressure. Which molecular formula could the organic compound have? Now, what we're saying here really, and what this is relying on, is our understanding of the ideal gas, and that an ideal gas at the same temperature and pressure will occupy the same volume. So if we've got 40 centimeters cubed of carbon dioxide and 40 centimeters cubed of water vapor, that must mean that they are existing in a 1:1 ratio of H2O to CO2. Now, if we look at this in a bit more detail, we should be able to see that this ratio here, the H to the CO2, is actually a 2:1 ratio from the hydrogens here to the carbons here. So what we're looking for is a molecule that has a 2:1 ratio of hydrogens to carbons, and we should hopefully be able to see that that is C2H4O. We then have a look at question 4. We're looking for which molecule here is a Z isomer. Now, this is looking at Carn-Ingold pre-log nomenclature, and we should remember that a Z isomer has the two highest priority groups on the same side. Now, remember, priority is assigned based on atomic number. So we're looking at here, if we have a look, we've got a 6 and a 1. Can't be that one, as we've got fluorine down here with 9, so these are our two high priority groups. If we have a look at this next one, we've got chlorine here with 17 and fluorine with 9, whereas down here we've got hydrogen with 1 and carbon with 6. So these two are the high priority groups and they are on the same side. If we have a look at the other two molecules that we have here, here we've got fluorine and chlorine. They're on opposite sides, so that's an E isomer. And similarly over here, we've got this carbon and this fluorine here on opposite sides. So actually again an E isomer, and so not the one we're after. So we want B because the two highest priority groups are on the same side of that molecule, the same side. So which type of reaction has the greatest atom economy for question 5? I've got here a substitution where, like with sports, if you put a substitute on, you're adding something in whilst also taking something out at the same time. We have a hydrolysis, which is a splitting, an elimination, which is where we're kicking something out, normally to form a double bond. We have an addition reaction. Now we should hopefully remember that atom economy is worked out by how the formula masses of the reactant compares to the formula mass of the desired product. So that should tell us that we're actually here looking at D as having the highest atom economy, because in an addition reaction, all of the atoms, from the reactants end up in the product. So if we have a look at question 6, we can see here that you've got 4 atoms, 1 to 4, labelled in the structure below. Which atom has a trigonal planar arrangement of bonds around it? So this is a classic question that we see crop up in organic chemistry papers. For something to have a trigonal planar structure, we can start eliminating certain atoms, because trigonal planar must have 3 bonds or 3 bonding regions coming off it. So that's immediately atom 1 out of the way there, because that's got 4 bonding regions, 3 hydrogens and a bond to another carbon. It's also atom 2 out, because atom 2, as you can see, has 1, 2, 3 bonds to the 2 carbons and nitrogen, and then another bond to this hydrogen. Whereas if we look at nitrogen up here, atom 4, and carbon, this carbonyl carbon here, atom 3, they both have 3 bonding regions. Now, for something to have trigonal planar geometry, it has to have 3 bonding regions and no lone pairs. And we should hopefully remember that an nitrogen has a lone pair. So what we'd actually see here would be a nitrogen with a wedge bond coming out there to a H, dash bond going back into the plane of another H, because there's 2 electrons there in that lone pair. So atom 4 is out. It's this carbonyl carbon here, atom 3, which gives us the answer C. We come down here then. Which molecule is a secondary amine? Question 7. So straight away we need to start identifying which are amines. Now sneakily, OCR has put some amides in here to throw us off. So 2 of the most common mistakes would have been selecting B here, but B is an amide. It's got that amide linkage going on just here. Also C is an amide, so that also has the amide linkage. So a common mistake here would have been, I think, to select B, because that nitrogen has got 2 bonds to carbons coming off of it there, but that's actually an amide, not an amine. So that leaves us with A and D as our options, and hopefully we can see that D is a tertiary amine, because this nitrogen has 1, 2, 3 bonds to carbons, and that then, by process of elimination, must mean that A is our secondary amine, with its bond to 2 carbons, 1 there and 1 there. Right then, so this seems on the face of it quite a complicated question. We've got quite a large molecule there for question 8, and it's asking for the number of chiral centres in the molecule below. Now remember, a chiral carbon must have 4 different groups or 4 different atoms bonded to it. So, and each atom or group bonded to it has to be unique. Now this means that straight away we can forget about anything in this benzene ring. Because remember, benzene rings only form, the carbons in benzene rings only form 3 bonds. So there will be no chiral centres there. Now, what we might find difficult about this structure is it's skeletal, so we can't see all of the hydrogens bonded to carbons here. So what I'd do in this sort of situation is I'd go around, and anywhere where there should be a hydrogen, I would draw the hydrogen in. And you can do this. This is your test paper. So we can see we've got hydrogens here. So we've got there are carbons. You're going to have CH3 groups on the end here. Always handy to remind ourselves that there is a carbonyl carbon, so that won't have a hydrogen. This one here will. And we should then see actually that the chiral centres become somewhat more apparent. So if I can highlight those chiral centres here, we've got one there, we've got another one here, one here, and our final one is down here. You can see that these are chiral centres because now that we've drawn the hydrogens in, it should become quite apparent. We've got 1, 2, 3, 4 unique groups coming off of that carbon. 1, 2, 3, 4 on this one. 1, 2, 3, 4 on this one. And again 1, 2, 3, 4 on this one. So the correct answer here is answer C, which is 4 carbons and 4 chiral centres. So it's quite a challenging question. But the best thing there is to take your time, look for where you think there should be hydrogens bonded to some of those carbons, and add those in on the diagram. And that makes it a lot easier to see where we should be looking for them. So if we move on to question 9 now, the molecular formula of the compound below. This is another example where on the face of it, it could actually seem quite simple, but students quite often make mistakes here because they forget about hydrogens, and skeletal structure throws them off in that regard. So what we're looking at here is actually C. And if I take you through, that should hopefully become slightly more apparent if it's not already. We've got 1, 2, 3, 4, 5, 6, 7 carbons. Remember, any point on here on the skeletal structure will be a carbon. And then from that, we should see that we've got a CH3 here, CH3 here on the end. And then we're going to have another hydrogen here, and each of these others will contain, or will have bonded to them, 2 hydrogens per carbon. So if we count those round, we've got 3, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that makes it C7H14. We could also use our general formulas there, but the general formula of cyclic compounds isn't something that you are required to know. So it's always good to double check by just counting round in this fashion. Right, question 10. We're over halfway there, ladies and gentlemen. So equal amounts of the 4 compounds are added to the same volume of water. Which compound would produce the most acidic solution? And they've given us here 4 options. So we've got what would appear to be a primary amide, a carboxylic acid, an ester, and an acyl chloride. Now, one of these we should be able to get rid of straight away, and that should be our secondary amide. This would actually act as a slight base because the nitrogen on there can donate a pair of electrons to a proton. Now, the 2 obvious answers to consider here are the carboxylic acid and the acyl chloride. Now, the acyl chloride itself hasn't got a proton which it could dissociate. So it might be that a lot of people would dismiss this. But what we need to remember is acyl chlorides actually break down in water to produce the carboxylic acid and hydrochloric acid, or hydrogen chloride. So your answer here is D, because this is going to break down to form a carboxylic acid. I might regret trying to write this. So that's going to form a carboxylic acid and HCl. And we should hopefully all remember that HCl is a strong acid. Very strong. So as that is a strong acid being produced, that would be at a much lower pH than the carboxylic acid given in B. So our answer here is D, the acyl chloride. So remember, acyl chlorides break down to give hydrochloric acid and carboxylic acid when they are added to water. So question 11. The compound below is analysed by 1H NMR spectroscopy. So 1H NMR spectroscopy, we're looking for different proton environments. How many peaks are observed in the 1H NMR spectrum? So what we should be doing here is thinking, well, how many different environments are there that a proton could exist in this molecule? And the first thing to do when we're considering this is look for any planes of symmetry. So hopefully we can see that this molecule is actually a mirror image of itself. And we have this line of symmetry going through this central carbon just here. So with that in mind, where are the protons? Well, we should see that we've got a proton on this hydrogen, on this hydroxyl group, We won't have any here, but we'll have 2 here. And there'll also be another 2 on this central carbon. And this will be repeated on this side of the molecule. So due to that plane of symmetry, there are actually only 3 proton environments on this molecule. So the answer that we're looking for here is C. Right then. Question 12. 0.1 moles of the following compound are reacted with 0.1 moles of aqueous sodium hydroxide. How many molecules of water are formed? So we have here a dicarboxylic acid, because we've got the two COOH groups, and that's been reacted with sodium hydroxide. Now we should hopefully see that this would react in a 1-to-1 ratio. Only half of these molecules are going to be able to react. So with that in mind, we can determine that the limiting reagent is going to be our sodium hydroxide. So that is limiting. So however many moles of sodium hydroxide we have, that will tell us the moles of water that can be produced. So our moles of sodium hydroxide equal our moles of H2A. Now, if we look at that, we've got 0.1 moles of sodium hydroxide, so we're going to form 0.1 moles of water, and then we need to know about how many molecules that is. So remember, a mole contains an Avogadro's constant of any compound, of any molecule or atom. So if we've got 0.1 moles of water, that must mean that we have 0.1 times Avogadro's number, which is A 6.02 times 10 to the 22. And I think a common mistake that a lot of people would have made here, they're either going to have assumed a complete reaction so that they'll get a large amount of water being produced, or they might have not done their multiplication correctly and ended up with an actual Avogadro's. But the sodium hydroxide here is the limiting reagent, so that's the one that's going to control the volume of water and the amount of water produced. So in question 13, which reagents would be used to produce this compound? So we've got CH3, CH2, CON, HCH3. And what this is really saying is, well, it wants you to realise what functional group is present in this molecule and then say how you would have produced it. So if we draw this out, I'm organic chemists, we love to draw everywhere, structures, wonderful. So we've got here CH3, CH2, C, O, N, H, CH3. Now to me, what immediately stands out here, if it didn't from the structural formula, is that this is an amide. So what the question's actually asking is, which of these four possible pairs of reagents could have been used to produce an amide linkage? And hopefully we should be able to see that that is A, because we have here an acyl chloride reacting with a primary amine, and that would give us the amide that we see in the question. Common mistakes here may have probably been, I think, if we're going to make a mistake, we might have gone for D, but I can't say for sure. If we look at 14, nearly finished now. Ethane reacts with chlorine by radical substitution to form chloroethane. Which radicals is or are present in the mechanism? So this is really asking you to think right the way back to when we looked at homolytic fission and the radical reaction mechanism to form haloalkanes. And what we're looking for here is C. So only 2 and 3. So remember, if we draw it all out, we're starting off on our Cl2 here, which with a bit of UV light is going to form for us 2 Cl radicals. So that is our initiation step. And then we should hopefully remember that once you've got your Cl radical, that is going to react with ethane, and that is going to form C2H5 radical plus HCl, and this C2H5 is then going to go on and react with another chlorine molecule this time. So let's get my unpaired electron there to form C2H5Cl plus a Cl radical. So as we can see, we do not at any stage form a hydrogen radical. So the answer here must be C, only 2 and 3. Final question on this multiple choice part of the paper now. which compounds is or are structural isomers of C6H12O2? And they've given you here 3 options: hexanoic acid, ethyl butanoate, and propyl propanoate. As always, it's organic chemistry. First things first should be to draw them out. So I'm going to use skeletal structures for this one. So we've got 1, 2, 3, 4, 5, 6. And if we pop a OOH group on the end there, there's hexanoic acid. Ethyl butanoate. So remember that ethyl tells us that that was made from ethanol, and butanoate would be butanoic acid. So we've got here a section like this. That's our ethyl, and then that's going to go to butanoate. Butanoate having 4 carbons in it. So we've got 1, 2, 3, 4. And then finally, propyl propanoate. So that's going to be made from propanol and propanoic acid. So we've got 1, 2, 3, going to an oxygen there. And then we've got our propanoic acid, form of propanoic acid, 1, 2, 3. And then it's saying, so which of these basically have the formula C6H12O2? Because remember, structural isomers have the same molecular formula but different structural formula. That's one of those definitions that we really need to learn. So same molecular formula, different structural formula. So we can see here that this has got 1, 2, 3, 4, 5, 6 carbons, 2 oxygens, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So hexanoic acid, yes. Ethyl butanoate, let's have a look. We've got 1, 2, 3, 4, 5, 6 carbons, 2 oxygens, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So ethyl butanoate, it's another yes. And finally, if we look at propyl propanoate, we've got 1, 2, 3, 4, 5, 6 carbons, 2 oxygens, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So another yes. So therefore, which of these compounds are structural isomers of C6H12O2? The answer is A. It is all of them. So the problem with this multiple choice part of the paper is lots of people spend a lot of time on it when really they should be coming back to it later on if they're getting stuck. It really tests how well you know the definitions and know how to apply your knowledge. So without lots of revision and real good knowledge of the basics, it's quite easy to get stuck in this or to make silly mistakes which can then hold you back later, because these 15 marks can give a good chunk over to your final grade. So my advice whenever you approach these questions is don't be afraid to draw all over the paper as long as it's relevant. Quite often when I get a paper, I'll start sketching out structures. I'll be writing down equations that I think I'm going to need. I'll be sketching out and predicting NMR spectra. It's your paper. Use it in a way that means you can answer the questions. But ultimately, if you find yourself really stuck on a multiple choice question, individually, they are only 1 mark each. So you are better to leave them, have a go at later questions, and then come back to these when you have time. But I hope this has been helpful. Join us for the next video where I'll start looking at some of the longer form questions starting with number 16. Thank you very much for listening.